In physics, there are four fundamental forces of nature. The first one is called the strong nuclear force. The strong nuclear force is going to be the force that actually holds things like the nucleus of an atom together. It's going to be a force between what we call quarks. Quarks are extremely small subatomic particles. They're the ingredients that make up things like protons and neutrons. And they're driven by something called the color force. There is an equation that describes this, but it's very complex. We don't need to know it. And it basically tells us that this type of force drops off extremely quickly with distance. The second type of force is the weak nuclear force. This force is involved in radioactive decay. It is very complex and likewise has an equation that we don't need to look at. It is far too complex for our current level. But it bases everything around what we call the flavor of a subatomic particle. As we get smaller and smaller, we tend to get more interesting descriptive words. The third type of force is one that we've actually seen before. This is going to be the electromagnetic force. This one is governed by electric charges. It is responsible for electromagnetism, which is the thing that makes magnets run. Then we can make electromagnets. It's responsible for the motion of electrical currents, which allow us to have electricity flowing through outlets, through light bulbs, all kinds of things like that. And we've actually seen the basic equation for this. It's Coulomb's law, which we studied in chemistry. Coulomb's law is going to be a constant along with a couple of charges that is based on the inverse of the distance squared between those two charges. So this 1 over r squared makes a significant difference as we move away. The final force, the one that we are going to focus on in this unit, is going to be the force of gravity. Call it gravitation. Gravitation is going to be dependent upon mass. Where the strong nuclear force is dependent upon a color charge, the weak nuclear force is dependent on something called flavor. The electromagnetic force is dependent on electric charge. Gravitation is dependent on mass. And it is represented by an equation that we call Newton's law of universal gravitation. It's represented like this. Now, gravitation is very interesting because it's going to occur between any two objects that have mass. However, on smaller scales, like even between two people, it is going to be so small that it's almost unmeasurable. But between two people, there would be a force of gravity that would be an attractive force. You could try and pull those two together. But we really start to see it take hold when we get to the size of things like planets. And what we are going to be looking at is the force between things like planets. Now, we've used a specific number before. This lowercase g equals negative 9.8 meters per second squared. That was the acceleration due to gravity. Now that we know Newton's law of universal gravitation, we can prove why this exists. What happens here is because F net equals mass times an acceleration, what we can really say here is that if we have two objects, let's say the Earth, which is a big blue ball in the middle of space, and we have a little person standing on that. Boop, boop. Well, that person has a mass. We'll call that mass 2. We'll give Earth the larger of the masses, the honor of being mass 1. Then when we put these together in that universal gravitation equation, what we get is F equals G. I'm gonna put these in different colors. We're gonna get F equals G m1 m2 over r squared. Now, G is a constant. We'll talk about it in a little bit. R is going to be the distance between those. But what we also can put in here is that what's the force that this person is experiencing because of that gravitation? Once we make the person, the object, this mass, the context, once we make that our frame of reference, we can replace this F with this F. And we can say that m1, I'll use another color, I'll use another green for this, times acceleration equals big G times the mass of the Earth times the mass of the person, all over r squared. And when we do that, well, this should have been m2. When we do that, this m2 divides out with this m2. And we end up with a constant acceleration based on the mass of the Earth, the gravitational constant, and the distance away from the Earth, equaling a specific acceleration. It's going to be regardless of that mass. And so now we can see why the mass of an object doesn't matter. They all fall at the same rate, because this universal gravitation is going to lose the mass of that second object. And so if we do these calculations, we should end up with a negative 9.8 meters per second squared. And this lowercase g, this is what we call a gravitational field. The technical name for this is the local field of gravity. And it's going to be unique to the planet. Jupiter would have its own, Mars has its own. Mars is actually about 30% of Earth's. And so when we look at this, this is what we call a field. A field is going to be due to one of those universal forces. If I were to compare this with the electromagnetic force, let's say I had something like a charge just floating out, just a pile of protons hanging out that has this big positive charge, there would be an electric field around this, where if another charge got caught in that field, it would be under the force of this charge. So when we say a field, what we mean is that there is the potential. So let's write this. When we say field, it's an area A field is going to be an area where there is the potential for a fundamental force to act. So when we talk about Earth having a gravitational field, it's really the area around Earth where the Earth's gravity is going to be the reigning force, where the gravity of Mars would be way out here and it wouldn't really make much of a difference on the Earth. In this area, it's the Earth that matters. So that's a lot of vocabulary and information to throw at you. But let's talk about this equation a little bit, because this is really the focus that we're pulling out with here. This F equals G m1 m2 over r squared. In the next video, we're going to practice using this a little bit. We'll actually calculate that negative 9.8 meters per second squared. But the last thing I really want to talk about here is how this value was determined. This G is a constant. It's going to be a constant 6.67 e negative 11. That value was not determined by Newton. Newton was able to put this equation together, but he knew there was going to be some constant that determined all of this. Newton was able to basically collect data from another scientist, Johannes Kepler, who had developed 3 laws of orbital motion, but wasn't able to fully prove an equation that could describe gravity. The closest he was able to get was that the period of an orbit was proportional to the radius of that orbit. But Newton was able to put this equation into a fully fledged form. But it was another scientist years later by the name of Cavendish who was able to prove that this number is the actual number for G. Cavendish did this with this fairly sophisticated experiment. He had 2 balls of significantly different masses, and this ball right here, this one right here, this was connected along this rod to a string. And this string would twist as there was this slight attraction, because these 2 balls, no matter how massive you have them on the Earth, the force of gravity is going to be small. He was then able to fire a light source at a mirror, which would twist with that wire a certain angle, and by measuring that angle, he was able to derive 6.67 e negative 11. So he had this very interesting setup with these 2 spheres, these 2 sets of spheres, that had this tiny force of gravity and just twisted ever so slightly. And so in the next video, we're going to do some calculations with this. we're going to see kind of what the limitations are. We're basically going to get to know this equation a little bit better.